Hello, everyone. This lesson, we are going to be looking at a very classic physics thing to think about, and it can be pretty tricky. It's called projectile motion. And so we are going to, I'm going to show you an activity that you can go through yourself, actually. It's an app you can download. I don't think it's free anymore, though. It used to be free, but look into it if you want to try it. But I will show you the results that you would get from it if you were here in person and going through an activity in real life, kind of thing, right? Rather than just sort of learning vicariously, if you will, or virtually through online delivery of this. So we're looking at another situation where X and Y components really need to be thought about as separate things. So when you have projectile motion, is when you have an object that's freely flying through the air. It doesn't have any wings or thrust or anything. It's just a rock thrown through the air or a ball thrown through the air and so on. So even actually the ball shouldn't have any spin because that actually causes lift effects, which you'll see later on. But yeah, so it's just an object that's launched at some initial velocity and it just travels freely through the air, which you remember from grade 10 makes a quadratic path. So students of mine in grade 10 definitely saw stuff like this and did a quadratic match, quadratic regression, and so on. So the program we use is called Vernier Video Physics. So it looks like that if you want to get it in the App Store. So basically you hold the iPad nice and still. If you're using a phone or an iPad or whatever, you hold the iPad nice and still and you get someone to toss an object, a ball or whatever. And so if this is your video screen, like what you're seeing, you hold it still, the ball gets tossed with some velocity, and then you see the ball travel through the air and land. Okay. In the video and the analysis, the software and so on, it allows you to pinpoint the spots that the ball was at any time you want. Okay? And you don't even actually have to label it in even time intervals. It'll analyze where they are and just graph them appropriately, right? So you can isolate where all those spots are. And then what it does is it analyzes everything about it. So it analyzes the horizontal velocity based on the horizontal locations and times. So this would be the X stuff. And it also analyzes the vertical stuff. So the vertical locations of all of these spots, right? So this information here would be able to give you vertical information and so on. So it's a pretty neat program. These pages sort of just give you an idea of how to do some of it, but because we're not doing this physically together, we're just going to see the results, right? So based on your results for projectile motion, you want to be able to look at it and say, okay, so how do you describe the vertical motion of the ball? How do you describe the horizontal motion? Explain why this is, okay? And then what does this mean about vertical and horizontal components of a velocity in projectile motion? And then describe the effect that gravity has on the components of the object and so on. These are a little bit redundant, but I mean, it gets the point across, okay? So if an object is freely moving through space just under the influence of gravity, what effect does gravity have on the X component and the Y component of the velocities? Okay, so when you actually take the video and get all the dots and so on, this is the kind of result you can get. Let me just pause quick here and I'll make sure to get that video quick for us. All right, here we go. So this is a video from EOSA or Lagasa or something like that on Rideau home turf playing BCI. So here we go. So I had my physics class in there and someone took this video and then those are the dots that got put in. And so you'll see a nice high set or a nice high bump actually. It turned out the bump was like pretty much going across in front of us. So you could, I don't know if it was a bump or a set actually. Was it a bump? No, it was actually a hands. It was hands both times for volleyball people out there. But anyways, there it goes. Looking at the spots, looking at those, and then obviously I didn't keep graphing at that point. Okay, so if you look at the first graph it gives you is literally just the X location and the Y location. It's literally just a trace of where it went. So the ball launched up and over and then up and and so on, right? And then got hit and so on. So while it's in projectile motion, it's analyzing here the X velocity, the x component of the velocity over time. So that's what we see. I'm not going to say anything yet at this point. Just interpret what that means to you about the x component of the velocity. Right? It should be an obvious thing to you here. Press pause, think about it, whatever. So what does it mean? Well, it means that it's traveling with constant velocity. You've got a straight line on a dt graph. So the horizontal velocity is constant while it's traveling through the air. Shows that the players had pretty soft hands. They weren't affecting the sideways velocity, the horizontal velocity at all, as they were just like popping it up and then popping it up again. Okay. Well, once it was popped up the first time, I should say, it had a certain velocity and it sort of kept that velocity the whole time, which is pretty interesting. It managed to do that. Keeping going, then the next graph it gives us is the x velocity. Well, we already know it's constant, right? So within pixel errors here, it's zoomed way in, basically. What you have is about this velocity, about 200 and something pixels per second, it says, right? So pretty much the horizontal line we'd expect, okay? Then we go to the next graph it shows, and it shows the, it shows the dt graph for the vertical stuff. And so obviously the vertical stuff, it gets a fast, it ends up going up and then down and then up and then down, right? If you notice here, the slope is steep, so it's fast, and then going to a slope of 0, so it's stopped, and then slope's increasing again, so it's increasing its speed, it goes down, and then slope, goes back up again. Now all of a sudden it's up with this upward slope velocity. We're working backwards here, which is awkward, but it's totally doable. Just too cool of a video not to use it. And then the final here is your VT graph stuff. And so the VT graph, notice that while it's in projectile motion, we have a nice straight line on a VT graph. What does that tell us? Remind yourself, look through your notes, press pause, whatever you got to do, think about it. You should be able to tell this answer right now. If you can't, you need to ask for help, right? So the result here is that it has uniform acceleration, right? Over time intervals, the velocity is changing uniformly, right? Well, what rate do you think that's changing at? And obviously the acceleration due to gravity, right? So the vertical component is accelerating due to gravity. The horizontal component is not. Okay, it's just the way it is. And a lot of people look at a ball going through the air and they think, it's speeding up and it's slowing down. How can the horizontal velocity be constant? Well, it's because the horizontal velocity is completely perpendicular to gravity. Gravity doesn't change the horizontal velocity at all. It changes the vertical velocity. Okay, so that is just reality. Rito won that tilt 2 straight games. Sorry, BCI students, but it's just that what happened in 2016. That's all. There was a force to be reckoned with them that year. They had a player named Brett that was just a machine. So horizontal motion, we obviously concluded that it's a nice straight line, and so it's completely independent. It's nice constant velocity, right? And then even here, where there is that constant velocity. And then the vertical stuff, obviously, we got curved lines showing you got changing velocities, and then you got these beautiful, nice straight VT graphs showing uniform acceleration due to gravity, right? So the summary is, of course, that we're seeing that the x components and y components of velocities are 100% independent of each other. Gravity is only in the y direction, and so it only causes the y component to change. So you need to be able to separate them out and deal with them separately and appropriately. Explain why stone vertical. These are just good concept questions. No actual work done yet. Soon, just to get us ready for the idea of it, soon we're going to be saying, okay, well, what happens if the first version we're going to see tomorrow is called horizontal projection? And we're going to have a ball just rolling along with, say, a velocity of like 10 meters per second. And so we're just going to look at, what happens, right? So if this is launched from a height of 5 meters at 10 meters per second, we'll be able to analyze out the path that it takes, and more specifically, really, how far over it lands, what velocity it hits with, we'll be able to get all these things. How long it takes to land, and the reason we're going to be able to do that It's because we're going to be able to think of this thing as having zero y velocity at all, and it has a constant velocity the whole time on its way across. It has this same horizontal velocity all the time, right? Whereas the vertical velocity would have started at zero, and then it would have gained a little bit of a vertical velocity, a little bit more, and finally landing, right? So basically, vertically in the y direction, we've got a uniform acceleration question where we've got v1y equals 0, acceleration in the y direction equals 0, and displacement in the y direction needs to be -5. Notice that that's just a uniform acceleration question. We can get the time, and we can get, so delta t, and we can get v2y. We can get those just with uniform acceleration work, right? And if we know how long, this is ahead of what we're doing today, but I'm just trying to get you ready for it, right? You have how long it takes. Well, if you have how long it takes to fall, well, that's the same amount of time as to travel sideways, right? And so the time number from here can go in here, and you know the velocity because it's 10 the whole time. And so you can calculate how far over it lands. Like, you can do all these things. So we're going to be doing that in detail in the next video. But for now, you're just answering key concept questions to do with stuff like this. Okay, so that's what we're headed towards. Nice, easy bit to hopefully, well, with understanding, it's easy. So I'll let you give that a whirl and ask for help if needed. But no calculations really here. Just key concept understanding bits for you. All right, that is it for now. Thanks for watching. Until next time, see you later.